Hello everyone. Today Roberto Hernández, Palomares from University of Waterloo will tell us about quantum graphs, subfactors, and tensor categories. Roberto.
Thank you so much. Thanks for the introduction. I should say, well, thank you all for being here. I'm quite excited to be talking at a graph theory seminar. I am an operator algebraist by training, so my field is properly functional analysis with a mixture of quantum theory and category theory. So it's a pleasure for me to try and branch out and hopefully invite some interactions. Now, this being said, understanding that perhaps I'm a bit foreign to this field of algebraic graph theory. Perhaps the language will be somewhat different. I'll try to do my best to be as conceptual as possible, not to turn the talk into a very dense or loaded with terminology, but rather the ideas and the examples. But if at any point you need more clarity or you need or you want to ask a question, by all means, please interrupt. So today I'm going to talk about the interaction of graphs in the quantum setting, subfactors and tensor categories. And this is a paper we put out recently. This is Mike Brannon and myself. In case you want to reach out regarding the contents of this talk, I am leaving my email up there. So again, feel free to contact me later on if you so desire. So let's start by perhaps discussing the very core idea of quantum graph, which is a non-commutative version of a classical graph. And I'll expand what can be made non-commutative about a graph, which in principle, I'm going to signal with this dotted line. Hopefully it's visible. Yep, I see it there. So in principle, a graph, and I'm thinking finite, simple graph, is just a finite collection V of vertices and a finite collection E of edges. So we will learn how to make this non-commutative in some way. But before we do that, perhaps let me convince you it's worthwhile. So what's the motivation? And there are plenty of sources of motivation, and I'll bring up some others later on. But in no order of importance, the inspiration to think about quantum graphs comes from various directions. One being quantum information. We're in the study of quantum channels and their capacity for zero error communication, say transmitting the capacity of transmitting a message, keeping noise under control. It is that quantum graphs naturally arise as the mathematical gadgets that would encode this level of communication. And this stemmed from work of Duan, Severini, and Winter back from 2016. They also arise in the study of non-local games, which are a mathematization of Bell's inequalities, which somehow quantify levels of entanglement in quantum mechanics. And here I will base my talk more in the work of Musto, Reuter, and Verdun from 2018 and 19, and the work of Michael Brannon and collaborators from the past decade. Also, perhaps closer to my heart is inspiration from operator algebra, where quantum graphs are natural solutions to the question of what would be the Cayley graph of a quantum group. This is a vast generalization of the classical groups we learned in abstract algebra. And here there's been work done by Vernieu since 2005, and more recently by Wasilewski last year. And also independently, there's the work of Nick Weaver, where quantum graphs arise as, again, natural means of formalizing this idea or quantizing a relation, right? So you have a bunch of points in a set, you define a relation. Well, there's ways to quantize this, and the solution to do this is in one way or in one shape or another, a quantum graph. So point here being is quantum graphs are the confluence of many different ideas in various different fields. So hopefully, so actually the part of the core idea when we started this project was trying to come up with a unifying framework to somehow invite all of these different inspirations, fields, and formulations into one single unifying concept. So let me scroll down, keep going. Before we get into it, let me describe the goals sooner rather than later, the goals of this talk. Essentially, I want to present the two main theorems of our paper, Theorem A and Theorem B. The first one is that every quantum graph will be made concrete. So perhaps with all this motivation and this vast source of inspiration, you might think that quantum graphs will end up being something quite abstract. And in a way, you will be right. But in this happy interaction between quantum theory, subfactor theory, category theory, we'll be able to actually write down every single quantum graph we want to think of to whichever level of detail we want, if we so desire. So quantum graphs will end up being rather concrete. And here by a subfactor, I'm not assuming everybody knows what this is. A subfactor is nothing else than an inclusion of non-commutative algebras, which can be commutative if you want, but that's what a subfactor is. So quantum graphs will be modeled over non-commutative algebras or inclusions thereof. So that is the main, the first main goal of my talk. And the second will be to establish a categorified or a quantum version of Frucht theorem, which is this classical theorem that's it's like 85 years old. Which I'm highlighting here in purple, that tells me that essentially to represent any finite symmetry, one-dimensional objects suffice. This is to say that for every finite group, there always exists some undirected, simple finite graph G, such that gamma is exactly the automorphism group of the graph. The proof of this is rather combinatorial, but essentially it's broken down in two steps where you first cook up the Cayley graph of gamma and then clean it up a little bit to actually achieve this isomorphism of groups right here. And the idea would be, since we are announcing that we have so much examples of quantum graphs, the idea is to prove that they are abundant enough to provide grounds for a quantized version of this theorem. And so is the point of Theorem B, where if we restrict to, well, instead of just thinking of finite groups, we think of finite quantum groupoids. We need them to be quasi-triangular. This might end up being a technical crutch, which I will describe later on, but it's rather general. There's a question. I hear somebody. All right. So the point is, every such finite quantum groupoid will arise as, quote unquote, the crossing quantum automorphisms of some quantum graph. I will make some of these terms more precise later on, but the idea you should keep here is this is a way to quantize Frucht's theorem. All right. So let's start simple, easy. Let's think of simple finite classical graphs. So when I say classical, I mean the graphs of vertices and edges from high school. So again, G is a collection, V of vertices and E of edges. So through a gadget that we use in operator algebras called Gelfand duality, turns out that for us to encode topology, we use C-star algebras. C-star algebras are closed subalgebras of bounded operators on a Hilbert space. But the point is, if you want to encode the topology of a space, you can instead think of a non-commutative algebra. And if so it happens that the non-commutative algebra is actually commutative, then this recovers the topological spaces, the Hausdorff classical topological spaces we can draw on a piece of paper. So the idea would be to push graphs through this Gelfand duality and try to write them down in operator algebraic terms, and then use the abundance of non-commutative examples to somehow work our way to a definition of a quantized version of a graph. So what is this? Say for the classical case, I'll try to use this example as leverage, as an illustrative example to try and perhaps subliminally describe the final structure that we will use to support quantum graphs, which what we need is a quantum notion of a set and a quantum notion of the adjacency relation, so to speak. And formally, this will be a Q system, or also known as a C-star Frobenius algebra. And I'll tell you what that is in a second. And to do that, I'm going to work this example out a bit further. All right, so back to G, consisting of V and E. The way to encode this is using the finite dimensional abelian algebra C to the V, which is highlighted up there in green. And we need to choose a state, which I'm calling here omega. And essentially, a state is a collection of weights. It's just telling me how much charge each vertex holds. And typically, if we pick the trace, this would tell me that all vertices are indistinguishable. So you can think of omega being the normalized trace if you want. And to this pair, I will typically refer to as B here in blue. So B will be some finite dimensional algebra together with a chosen state. You can think of it as a trace again. And a way to capture the edges of a graph is to, or a way to write it down is through the adjacency matrix, which out of the assumptions we have will be a V by V square matrix consisting only of zeros and ones, essentially telling you who's connected to whom. Well, this is an adjacency matrix, which we will denote by T hat for reasons that I will make evident later on. So what is the structure behind this set? So the idea is I can use the state omega to complete my algebra B into a Hilbert space, which I'm calling L2 of B, which is essentially B itself. It has a dense copy of elements of B. I'm just rethinking of it now as a Hilbert space. And the point is, this space here becomes a bimodule, as in ring theory over B, where you can left multiply or right multiply vectors since they're already elements in B, right? So this is a B bimodule represented in L2 of B. And in this completion process that we performed, we can still push the initial structure. So for instance, here on top on green, I'm representing the extension of my state, which essentially just takes a vector, B omega. This omega simply is cosmetic. It's a decoration that allows me to distinguish a vector in L2 of B from an operator in the algebra B, but it's merely cosmetic. So what this map here does, which is a diagram which inputs, let me perhaps write it down, inputs an element in L2 of B and outputs a complex number and simply evaluates the state. In the case of a trace, this will just give you the trace of a matrix, say. In general, it's just omega of B. And here on the right, with this trivalent vertex, what I'm representing is the extension of the multiplication, which again takes two copies takes two vectors in L2 of B, multiplies them, and spits a vector in L2 of B. And by exact expression, it takes the vector B1 omega and B2 omega and multiplies it. That's just a representation of the multiplication, which graphically is very naturally this trivalent vertex. Now, the point of bringing Hilbert spaces to the picture is that we can compute adjoints of maps. So a map between Hilbert spaces always has an adjoint, which in finite dimensions, it essentially just corresponds to the transposition operation or the conjugation operation rather, which we do here. And what happens graphically is that this initial map, the state, gets reversed. So it inputs now a complex number on the bottom and will output a vector. And it's no mystery. Essentially, it just takes a complex number and decorates it with omega. That's what this adjoint map ends up being. This is a computation I'll save you from seeing. And also, you can adjoin the multiplication and obtain a co-multiplication, which will, in the abelian case, will take a vector and simply copy it. So it takes B and spits B tensor B. In general, for more complicated algebras, say non-abelian algebras, this co-multiplication will be more complicated, but here's just an example. Now, what you end up with here in blue is what I will denote by Q, which is this whole collection of the space L2B with its multiplication, its unit, its co-multiplication, and its co-unit. This turns out to be a finite dimensional, in this case, abelian, quote unquote, Frobenius C-star algebra, also known as Q system, say in the quantum field theory literature. And the structure that this collection has is that of an associative unital algebra and simultaneously a co-associative co-unital co-algebra. All of those coexisting together. But more is true. So this adjective of being Frobenius essentially demands that the co-multiplication map is a BB bimodule map, which means essentially it demands a compatibility of between the multiplication M and the co-multiplication M dagger, or M adjoint if you wish, which graphically is represented by that diagram in the middle. And the compatibility just tells me which verbally said this is a BB bimodule restriction. Essentially, I can deform the diagram as the one on the left or the one on the right, and essentially these will be the same as maps. This is the Frobenius condition, and moreover, another natural compatibility one can demand of these two maps is that if I first co-multiply and then multiply, what that will end up being is just some multiple delta of the identity map on B. And this condition is also studied in the, say, quantum groups literature, and this is called a delta form. This has been studied by, in the work of Banica and collaborators. And these are just the finite dimensional examples of our Frobenius or Q systems, Frobenius algebras or Q systems. So all of this is to say, perhaps I'll zoom out a little bit. All of this is to say that, well, whenever you take a set X, say, and you look at its automorphisms in various flavors, you get more structure, right? So the automorphisms of X, some set as a group, well, it always forms a group under composition. If you look at it as a linear structure, it'll have an algebra structure. So the fact that the endomorphisms of Q have the structure of an algebra under composition is perhaps no surprise. But here the main new feature is that using the Q system structure, we'll be able to endow this linear space end of Q, the endomorphisms of Q, with a second operation, which I'm denoting by a star there on the bottom, called convolution. It's also known as Schur product, depending on the various realizations you give to this. So this is this will recover the convolution from group rings. It's also the Schur product of matrices if you interpret your categories or your data, sorry, appropriately. And perhaps for those more combinatorially inclined, this structure, or this double structure on end of Q with composition and convolution, will conform into what's known as an association scheme. Now here in white on the left, I'm just representing endomorphisms of Q functions as black boxes, right? At the end of the day, functions are black boxes that take inputs and do something to them and spit outputs. So here, a generic element in end of Q will look up like a black box that takes an input from Q and spits something out of Q. And graphically, right, in this period of representing our algebraic operations diagrammatically, well, the composition is just a vertical stack. If I compose S1 followed by S2, diagrammatically, this just corresponds to the stacking. And the convolution, right, this new structure we just afforded. So S1 convolved with S2 essentially diagrammatically can be described by the diagram on the left. And perhaps I'll sneak in the corner here the formula for the diagram at the very left. Here, this is simply a co-multiplication followed by the tensor product of S2 and S1, and then you multiply, right? And that's a new gadget we just cooked up. I will tell you more about the utility of this key observation here. But let me perhaps now, again, look into the specific example of my commutative Q system, Q here, C to the V equipped with a trace, right? This is just a normal set with V many elements. If you interpret this convolution operation in this Q system, as I said before, so if you convolve S1 with S2 and look at the ijth entry, well, you will notice, and this is simply a direct computation, that the ijth entry on the left-hand side is the pointwise product of matrices. So if I convolve two V by V matrices, the result will be a V by V matrix whose ijth entry is the product of the corresponding entries of the original matrices. And this is known as the Schur product. And at once, this gives us the following realization. So if we have a V by V matrix, say with complex or real entries, and if you want to characterize those matrices which actually arise as adjacency matrices of a classical graph, well, essentially this condition demands that the entries of the matrices are zeros or one. Which equivalently can be written rather algebraically by demanding that T hat is a convolution idempotent or a Schur idempotent, right? Because that's the only way in which the entry-wise product can be 0 or 1 if every entry is 0 or 1. So that's an if and only if. And essentially, this just provided us with grounds to abstract and quantize the notion of a graph, as we only used operations that are afforded by any Q system we can think of. And so with that being said, we jump into the definition. A quantum graph G will now be a Q system, which I'm representing by this inclusion now of the complex numbers inside of B with the state, right? This is a summary of all the diagrams I put above. And this will be now a quantum set of vertices. Just a finite dimensional C-star algebra with a chosen state, together with a chosen convolution or Schur idempotent, which is meant to capture the adjacency. Now, before I go into perhaps more examples of these graphs, let me tell you that for any Q system you pick, abstract or concrete, you will always be able to find a complete graph on that quantum set, which I'm denoting by boldface K as a click, and also the trivial graph. And the set will be the Q system Q, obviously the vertex set, and the adjacency map of the complete graph will be the co-unit followed by the unit in this graphical sense here. And for the trivial graph, it'll simply be the identity map, which I'm representing with a strand. So this is the identity on Q. These two maps are always available on any Q system. So on any quantum set, there are quantum graph structures. So that's going to be important. Again, if Q here is C to the V, this map here is the matrix filled with ones. One can compute that. And so this actually recovers the usual clicks from, say, classical combinatorics or classical graph theory. All right. So now we will make a conceptual jump, perhaps a conceptual leap. And instead of talking about quantum graphs supported on finite dimensional structures, we want to categorify this idea. Perhaps fully abstract it, right? Fully think of it in abstract, nonsensical ways. And later on, we will turn them abstract. We'll turn the abstract into concrete. But for now, let me perhaps further the reach of our definitions and introduce the idea of categorified graphs. And perhaps the way to think about this is we want to define what it means to have a quantum symmetry equivariant graph. And the idea is, what's a quantum symmetry? Well, the algebraic gadget in encoding a quantum symmetry is known as a unitary tensor category. I'm not going to give you a definition. Instead, I'm going to give you some examples. Examples you actually know of. These tensor categories are actually no strangers to anybody. And morally, these tensor categories are meant to capture the idea of a discrete quantum symmetry. So they correspond to generalizations of discrete groups or compact groups, which are their duals. And this is to say some examples. Well, first, we have the tensor category Hilb or Hilb FD of finite dimensional Hilbert spaces, which is essentially the tensor category you can generate with the complex numbers, taking direct sums, taking tensor products, taking conjugates, as in the Rives representation theorem and whatnot. So this, of course, will contain C to the V. This will contain this, of course, will contain the n by n matrices and so on. So all the linear algebra we did as undergrads is essentially captured by the structure of the category Hilb. So again, this is not a stranger to anybody. We're just putting all finite dimensional Hilbert spaces with their linear maps all together, considered as a category. Another way to cook up tensor categories is simply by taking a discrete group. You can take a finite group if you want. And essentially, this will be the tensor category you generate by a collection of copies of the complex numbers graded by the group elements, where essentially if you multiply them, we have a tensor product. So if you tensor CG and CH, this will be the graded copy at CGH. So when I write gamma as a tensor category, this is what I mean. And of course, you can also take a compact group and you can take its tensor category of finite dimensional representations. This will be a prototypical example of a unitary tensor category. In full abstraction, an abstract unitary tensor category has essentially the same structure as this gadget right here. So in a way, doing tensor categories is doing representation theory, disposing of the vector spaces. We don't care about them that much. In any case, let me keep going and finally land at the definition of a tensor category or C equivariant quantum graph. So again, denoted by G, the quantum set of vertices will be captured by a Q system. So this will be some Q in the category, some abstract Q system internal to C, and we should think of this as a C equivariant quantum set, together with a Schur idempotent, right? So we need to pick an endomorphism internal to this category, an endomorphism of Q that actually satisfies this Schur idempotency condition, and use that to capture the quantum relation of two quantum points being connected by a quantum edge. So this is just a straightforward generalization of what we did, perhaps in much more generality and in further level of abstraction, but it's the very same idea of a classical graph. All right, time for examples. So let's expand the trivial tensor category. This is trivial because it's generated by the complex numbers, Hilb FD. So what are the Q systems? This is what are the classical and quantum sets that this category hosts? Well, as I've been saying, these are all the finite dimensional C-star algebras together with a choice of state, a faithful state. Take the trace again if you want. Now, of course, there's going to be a distinction, right? Some algebras are abelian, some others aren't. Those which are abelian here will correspond to the classical graphs. So you just pick some abelian Q system and a matrix of zeros and ones, which as we saw is a Schur idempotent. And this will yield all the classical finite graphs ever, period. And of course, there's going to be finite dimensional C-star algebras, which are non-abelian. Think, for instance, of n by n matrices or direct sums thereof. So these will be in general very non-commutative objects, but of course we can endow them with a Q system structure. We'll be able to pick and construct explicit Schur idempotents, and those will be, say, the quantum graphs that are perhaps closest in quantum information, or the most relevant in quantum information. And actually, the problem of constructing and classifying these graphs is super interesting. And for the case of M2, the 2x2 matrices, these were completely classified by Gromada and Matsuda a couple years back. So it's not a trivial problem to construct these graphs. And again, part of the point of my work with Mike is to shed some light on how to produce these quantum graphs on demand and make them concrete, right? So be able to write down their adjacency matrices. Now, before I move further, I do not want to waste this opportunity for a little advertisement, which again connects to the initial motivation on why to think about non-commutative graphs. So even before the parting, this category of Hilbert space equivariant quantum graphs, the usual quantum graphs, by work of Kaufman and Cooperberg, these are very, very closely linked to the knot invariants that were developed in the 90s, say the Kaufman bracket, the Jones polynomial. So the existence of highly regular classical graphs essentially yields evaluations of these knot polynomials, which help us tell them apart. And the idea would be to perhaps develop this project of realizing quantum invariance under now the scope of these enlarged quantum graphs. And this is a project I'm developing with my outreach initiative called Outsourcing Math Research. And the idea is to support young researchers in underdeveloped countries. Now I'm focusing on American countries. I'm currently working with undergraduates in Mexico, Costa Rica, and Colombia. And we're working on actually writing down explicit models for these quantum graphs and capturing the notions of higher regularity that will allow us to compute whether or not there are quantum analogues of highly regular classical graphs. For instance, think of the pentagon, think of the 9-Paley graph, think of the Higman-Sims graph. With the tools we developed here, essentially these questions boil down to computational questions, essentially. But the advertisement that I wanted to make here is to perhaps invite you to reach out to me if you're interested in this type of outreach activity. We are always short on mentors. We're always short on funding. We need funds. So if you would like to sponsor or to support in any way you can this initiative, you are very welcome to, and I invite you to please reach out to me. But in any case, this was just an advertisement. Let me carry forward with the examples. And here I want to present two of them in tandem. The two examples I gave before. Here on top, the representation category of some compact group. And here I'm just thinking of these gamma-graded Hilbert spaces, where gamma is a discrete group. On top, right, if you demand a concrete description of all the quantum sets for classical and quantum sets that can be hosted on this category, right, the family of Q systems, these will correspond to finite dimensional C-star algebras, which have an action of G. So some level of representation, actually, together with a chosen state, which is invariant under this action of G. And essentially, well, a graph in this category will just be some chosen G C-star algebra with a state together with a Schur idempotent. And again, from the quantum information perspective, from actually more specifically from the perspective of zero-error communication, these quantum graphs have already appeared recently in the literature in the work of Dominique Verdon last year. Now, on the bottom here, if you look into the category of gamma-graded Hilbert spaces, Q systems essentially correspond to taking a subgroup, lambda of gamma, together with cohomological data, which for simplicity, let me just suppress. So the quantum graphs that you could cook up in this category, you'll have to work this out a little bit, but these correspond to a choice of subgroup together with a subset of the group, and these are nothing else than Cayley graphs. So this further justifies our way of thinking of these quantum graphs as equivariant with respect to a symmetry. If you look at this category, we have systematically recovered all Cayley graphs. All right. Now, perhaps the question is, all right, so Q systems categories, but how to cook up solutions to this idempotency equation, T hat convolved with T hat equals T. Where do solutions of this equation come from? And the insight comes from subfactors, right? So this is a subfield of functional analysis. And I don't have the time to give you a rough introduction to this, so perhaps let me distill the most important ideas that we'll make use of and list a couple of facts. As I presented in my joint work with Mike Hargless a few years back, we show that every tensor category is actually concrete. So if you were thinking, okay, tensor categories is a lot of abstract nonsense, ethereal stuff, not quite. Since we're looking at the unitary tensor categories, we will always be able to embed them into a concrete object. So there's always going to be a unital C-star algebra A, which is actually constructed directly from the categorical data. And so that we can actually pretend that our tensor category is a full subcategory of the finitely generated and projective bimodules over A. A concrete way to think about this, perhaps loosely speaking, is once that you have constructed your C-star algebra A, which is a mixture of sophisticated techniques. Admittedly, you need pre-probability, you need planar algebras and whatnot, but essentially the category will look like all the the matrix amplifications. That this is all n by n matrices with entries in your C-star algebra. So essentially, doing tensor categories is the science of doing not linear algebra, but linear C-star algebra. Essentially, we're doing linear algebra over matrices whose entries lie in some ring, with a lot of properties, though. Nice properties. The second fact, also highlighted in my work with Wan Chuen, Corey Jones, and Dave Pennies, is that C-star algebras are Q-system complete. What this means shortly is that the collection of Q-systems in any given category actually can be realized in terms of inclusions. So you can include your base or your coefficient algebra A in some extension B in such a way that if you view B as a module over A, it'll turn out to be finally generated and projective over A. And what this means is B will be an n-fold amplification of A, perhaps cut down by a projection. And this is it. So Q systems correspond to inclusions, or finite inclusions, finite dimensional inclusions in quotation marks. So combining these two facts, this affords us yet another definition of a quantum graph, which we can always, let me insist on this point, we can always make very concretely. So a quantum graph will consist of a Q system, which is B viewed as an AA bimodule. You can think of it as the full inclusion if you want, A inside of B, together with some Schur idempotent contained in the endomorphisms of B, which commute with the left and right actions. Now, the algebra I'm showing here is, of course, infinite dimensional in general. So you might think all hope is gone, but rather the contrary is true, because restricting to this equivariant setting, these algebras here, these algebras of AA endomorphisms, turn out miraculously to be finite dimensional C-star algebras. So these are just direct sums of matrix algebras, making it rather possible to compute Schur endomorphisms, or Schur idempotents, if we know enough data about the category. Now, what this gives, furthermore, is a better graphical calculus for Q systems. So our Q system, our quantum set, we can always represent as a pair of pens. What that means is that instead of thinking of Q simply as this strand with its multiplication trivalent vertex and its state, we can actually use this inclusion of A and B to realize Q as a double strand. So here in the middle, we have shading. So let me zoom in here. So instead of writing Q, we represent it as a double strand that's indexed by the conjugate space to be tensored by B itself. And the name pair of pens comes from looking at what happens with the multiplication under this double stranding procedure. And the name becomes, or the nomenclature becomes self-evident. The multiplication just turns into a pair of pens quite visibly. And the state turns into this cap map, which is shaded inside and unshaded outside. And this apparently trivial illustration will actually take us quite far and help us connect the dots. And here's a key observation is that viewing Q systems or realizing Q systems as concrete inclusions always gives us dual categories. So from a starting Q system, we can graph the category it generates, which we will denote by C sub AB here on the left. Right, so it's a category generated by Q in disguise as B bar tensor B, which is essentially anything you can generate with a set of vertices. And the dual, which we are denoting by C, indexed by the inclusion of B inside some larger algebra B1. This is called the Jones construction, by the way. It's a systematized machine from subfactor theory. I won't tell you much about, but this dual category is actually what you can generate thinking of the edges as well as a quantum set. So this is the duality that appears here naturally. And so it turns out that this duality is a generalization of Pointryagin duality or even Tanakian duality between compact groups and their duals, or Hopf algebras and their representation categories. And again, for the combinatorially inclined people, this essentially closes the loop on actually allowing us to view endomorphisms of Q systems as pieces of association schemes. So what happens here is that if you view the endomorphisms of your initial Q and compare them with the endomorphisms of its dual, right? So if you compare the vertices with the edges, what you have is an isomorphism between them, right? So notice we're taking B endomorphisms on one end and A endomorphisms on the other, and we're switching the placement of the bar. So there is an isomorphism here that actually takes the composition and turns it in on the left and turns it into the convolution on the right, and vice versa. Takes convolution on the left and turns it into composition. And the map, actually, if you interpret this when C equals rep G, for instance, turns out to recover the Fourier transform, right? The usual Fourier transform achieving the Pointryagin duality. And diagrammatically, this map is really easy to write. We just take a B bilinear endomorphism, right? That's why it's shaded on the left and on the right. And here, this is a relative tensor product, so there's no shading in the middle, relative with respect to A in the middle. And it's simply just a rotation map, right? Just connect your cup and your cap and rotate the map. So T will get mapped to T hat. So the reason I was using T hat all along is because all the adjacency matrices are actually Fourier transforms of idempotents. So this is to say, if you restrict this transform to those maps which are idempotents, this will be actually a bijection with all those Schur idempotents on the right-hand side. And this proves Theorem A, essentially. All quantum graphs arise through this duality. And why is that? Because if we're searching for adjacency matrices on Q, all we have to do is look for idempotents on the left-hand side. And again, this turns out to be a finite dimensional C-star algebra. So this decomposition is always possible. Again, to give you a very concrete picture of what this would be in the case of groups, for instance, to find these idempotents corresponds to, say, computing the conjugacy classes of a finite group. Which is, if you want, a process you can perform. And this will exhaust all quantum graph structures you can impose on those categories. So yet again, this allows us to redefine a quantum graph as some inclusion together with a natural or a composition idempotent on the left-hand side algebra, which are presumably easier to find in various contexts. Now, how much longer do I have? We started a couple minutes off. I'm not sure if I have 50 or 60 minutes.
Maybe 5 more minutes.
All right. So I'll wrap up. Thank you. We have explained how to obtain theorem A. Let me just quickly glance through theorem B. And the idea is, let's take H to be a finite quantum groupoid. So this is a finite dimensional C-star algebra with a multiplication, a unit, a co-multiplication, and a co-unit, together with an involution map that mimics the inverse for taking inverses in groups. So this codifies finite dimensional quantum groupoids. And the idea is that these quantum groupoids correspond to, by taking the representation categories, to those tensor categories which are called fusion. And these are essentially finite categories. Now we will focus on quasitriangular groupoids, because so it happens that they correspond to braided fusion categories. And here, again, C is rep H. So a braided fusion category, it's essentially a tensor category where the tensor of objects is commutative, and essentially you can find a natural family of isomorphisms, which is represented diagrammatically by this braiding, that actually implements those isomorphisms. And the last fact that we will need to establish Frucht's theorem is that finite quantum groupoids always correspond to some inclusions, which are finite depth. This means the associated categories are finite. They are called hyperfinite in the sense that both algebras N and M are approximable very nicely by finite dimensional data, and again, finite index, as we have been doing all along. So this is a trend in subfactor theory where you try to reconstruct a subfactor from some type of algebraic data that we have on the left. I'm not going to go into the details. And essentially, using these tools, we can obtain rather easily a C equivariant version of Frucht theorem, telling us that every quasi-triangular H arises as the crossing quantum automorphisms of some categorified graph. And I'll give you the 1, 2, 3 steps of the proof as a sketch where, well, you start fixing your finite quantum groupoid. Let me show you the statement. And then you use the reconstruction techniques from subfactor theory to obtain an inclusion N inside of M, and then you look at its dual M inside of M1. And in the same way as what Frucht did in 39, you construct the Cayley graph of this system of symmetry, say. So now we consider G to be the complete quantum graph on M1, which is again a quantum set. And from the quasi-triangular structure, quasi-triangular means there is an R in H tensor H that satisfies the Yang-Baxter equations. We cook up the braiding, which I'm calling beta, right? It's this collection of maps here. And essentially, using this braiding, we'll be able to write down the representation category of H, which we now is equivalent to the representation category of this subfactor. So all we would need to close the loop would be to obtain an isomorphism between what we already have and say data on the left that could be interpreted as a quantized version of automorphisms of quantum graphs. So an automorphism of a graph is just a map. Let me put it as a black box that commutes, so a map F that commutes with the adjacency, right? So this is the usual definition of a quantum, of a graph automorphism. And in quantum informatic setting, a graph, we need to quantize functions in the same way that we quantize sets. That also comes with the notion of quantizing a function. And And what that boils down to being is now your functions f will look similar, but they will now have some entanglement resource, k. And this presentation is just to say that functions now become random, and the process of evaluating these random maps obeys a quantum probability distribution that is modeled over the structure of a Hilbert space. So the idea is we would want maps where we somehow can push T up and down that strand, just mimicking what we did in the classical case above. Turns out that gratings are natural solutions for this, right? So here, right, you can imagine that I'm pushing T under the top strand freely, and that follows from the naturality of the braiding. What we realize here is that the braidings that people have been studying in tensor category from an algebraic perspective actually yield examples of quantized adjacency preserving automorphisms of G. And simply say, if you take the braiding of an object over M1, and if you simply forget the braiding and remember the object K, turns out that this forgetful functor is actually a tensor equivalence. And so we can recover the original finite quantum groupoid in terms of the crossing quantum automorphisms of the original graph. And that's a sketch of the proof of Frucht theorem and everything I wanted to say. Thank you for your attention.
Thank you, Roberto. Do we have any questions? Earlier you mentioned that the Hilbert graphs correspond to some not invariant. Do you have some other special graphs correspond to some invariants?
Beyond the Hilbert space ones?
Yeah.
Not to my knowledge. Yeah, I don't know. The thing is, ideally, you would want some type of numerical ways to compute these polynomials. And what you want is to associate numbers to knots which are invariant under the knot moves, right? The Radameister moves. So these invariants are naturally encoded by a bunch of matrices with complex numbers that turn out to be adjacency matrices of graphs, and the topological invariance then becomes higher regularity in these graphs, right? And this is 1 regularity, 2 regularity, 3 regularity type of notion. But to be honest, I haven't thought about the problem at like higher versions of it, or maybe more complicated versions of those. But one can definitely make sense of that. I mean, one can speak of graphs in any crazy category that you can conjure up. So why not use them to, say, compute invariance of the underlying algebras or bimodules or whatnot? But I don't know if you had anything in mind, perhaps, or any examples you would want attacked in mind.
I don't have anything in mind now. Thank you for the answer. Ada has some questions.
So I don't know if this question makes sense because this is like way over my head. So for the classical case, if you have a spin model, then it has to come from a graph that is in an association scheme in the classical sense. So for this quantum version, does it have anything to do with Gomad's association scheme? Like the quantum association scheme that he has defined?
Yeah, quite a bit. So the search would be to of course, like start with the quantum set, which is going to be some multi-matrix algebra you want to use to support your candidate of highly regular graph. But of course, to cook up the adjacency data, right? So here perhaps will be the quantum set of interest. To cook up the quantum idempotent, you would need to use the Fourier transform and essentially look at the decomposition in blocks of that algebra on the left. And if so, say your Q system would come from, say, an abelian finite group, then this setting here is essentially boils down to the axioms of an association scheme. If that addresses your question.
So like for example, I don't like this question might not even make sense at all. Like, is there a quantum Hernández graph or quantum pentagon or something like that?
Work in progress.
Okay.
It's yeah. It's that's exactly what we're looking for. So the idea is, I mean, even in small dimensions, right? If you're playing with 3x3 matrices, the algebra on the left, I think, is dimension 81 squared. So looking for an appropriate presentation that will allow you to look at say central idempotents on the left hand side, take some work, actually quite heavy hands-on work. And only then you can say, all right, there exists a quantum pentagon or a hexagon or whatever it is you want. But this is essentially what. So with this quantum Fourier transform in hand, the question of asking, you know, is there a quantum analog of the Cayley graphs? Well, it's now a computational question using the transform I'm displaying right now. Yeah, right now it's work in progress. I think we're close to giving definitive answers to whether these small quantum analogs of regular graphs exist. But it'll have to wait a little bit more for us to give you definitive answers.
And if you don't mind, I have one more question. So in the classical case, like you like if you look at like Schur proved that if you look at spin model that gives you Kaufman's polynomial, then it has to come from like a two-class association scheme or three-dimensional kind of algebra. Is there like a kind of an analog result in the quantum version?
Yeah, again, that would be work in progress because so sort of the solution or the answer to the question would be in the same direction, where the spin model would boil down to the existence of a Schur idempotent on the appropriate Q system that satisfies the sufficient regularity properties, right? So one would have to make sense for a quantum graph to be triangle free, or for it to be connected, or for it to be a tree or whatnot. And actually using algebraic equations, you know, just equations involving t hat, composition, convolution, and tensor products, we can actually write down what one regularity, two regularity. We can write down a Laplacian. We can count the connected components on a quantum graph. We can count the number, or well, we can detect if it has cycles or not. So we can essentially play out a quantum algebraic version of algebraic graph theory. But the point is, one would have to show whether there are solutions to the problem you're posing or not in the appropriate Q system. And again, this is fortunately only now with the subfactor insights, a computational task, which I'm developing with my collaborators at OMR. Hopefully in the next few months, we'll have definitive answers. Computation is hard, turns out. But does that address your question?
Yes. I guess my next question, like for someone like me, where's a good introductory paper or book to read about this stuff?
Yeah. So I think the work of both Matsuda and Gromada,
Okay.
from 2022, they work out the theory for very small examples, which are already interesting. They actually work the smallest quantum example for 2x2 matrices. There's also the work of Musto, Reuter, and Verdon. The work of Mike Brannan with Brent Nelson and Ismert. It's like five authors. So that one also plays with the some of those finite dimensional examples. I was hoping that my own work was also accessible enough. So there's a huge section of examples. Hopefully you can also dig in there. Yeah, I think this is perhaps enough to keep you busy for a while. We also try to gather a bunch of references in the paper, so I encourage you also to pursue some of them if I'm forgetting about them right now.
Thank you very much.
Thanks for the question. I see there's a question on the chat, Maria. So does these theories simplify significantly once you allow finite dimensional entries? Yes. I mean, in a way, we shouldn't be scared of the infinite dimensional setting before I address your question, because there's so much symmetry or so much symmetrical restrictions that, again, all the algebras you're seeing in on screen are finite dimensional C-star algebras. And those are the relevant gadgets here, not so much the infinite dimensional non-commutative objects. But short answer is yes, it does, because essentially you can write down bases and you can get a much firmer grasp, say, on your Q systems and your quantum sets. And this is essentially what it's allowing us to move forward in this project with OMR and actually test, say, experimentally, if we successfully have recovered the notion of a tree, or the notion of connectedness, or the notion of being triangle free, being too regular, and whatnot. So the grasp of these algebras is now so firm that if you assume they're abelian, this recovers the classical such notions. If this was the intent of your question. All right, happy to. Thank you for the question.
Any other questions for Roberto?
Yeah, just a short question. It's like, could you spell MRV, so the spell the surname, so that I can find the paper? Yeah.
Yes. So here, Musto, Reuter, Verdon. The paper is titled "A Compositional Approach to Quantum Functions." And actually, they wrote a follow-up paper. This is from 2018. The follow-up is the year following, where they used the abstract algebra of tensor categories to cook up examples of quantum teleportation. Quantum pseudo-telepathy, I meant. Essentially playing with Morita equivalences of Q systems and whatnot. Further showing how good this framework is to encompass a bunch of quantum physical effects, actually. But this is the paper I've been referring to, if this helps your search.
Right, thank you.
Anytime. And it's on the archive, so it should be pretty easy to find once you have the title.